So thank you, Sarah. Thank you guys all for joining us at this event. I think Sarah described it aptly as kind of the Super Bowl for us. And I think Ari and Navi both set the stage really well for what I'm about to do. And they kind of gave this overall vision of innovation and really how we need to evolve, how we ultimately need to get better. So I get to take that idea and dive into a certain part of the problem, and that is really dealing with the front end of the funnel and finding ideas to put into it. So it's got a cute title, Weak Signals and the Search for the Next Big Thing. We're really trying to see how we can use new tools to do better at the first part of the innovation process. So I'm not going to talk about the entire thing. That's the level setting, I think, that Ari and Navi did to some extent. But I'm going to break this talk into 3 parts. First thing I want to do is talk about the value of detection. I think this is pretty intuitive. I'm not going to spend a ton of time here, but I do want to level set in terms of the importance of having a strong detection function in your business. 2, I'm going to dive into that actual innovation process and show how some of the tools, the way we're doing it, which hopefully inspire you to do it your own way, and how we can get systematic about discovery at the front end. And finally, how many people here have had an executive talk to them about wanting to use machine learning or AI? Is that happening in your business? Someone just said, go use the AI and didn't tell you what to do. We want to try and give you a little more direction, try and talk about how we can have a more tangible way to augment our innovation process with machine learning. So first, a question for everybody, and that is just what percentage do you think of product development projects turn into profitable products? Is anybody brave enough to shout out a guess? 8%. 8, 10. Very good guesses, actually. So based on a study by the Product Development and Management Association, the answer is about 12.5%. These numbers, you could calculate them any which way, but the bottom line is I think we'd all like to do better than that, and the number is probably even lower when you look at all the ideas that flow in. So we want better results, and we want to get to those results faster. That's really what we need to do as a community. Ari showed that graph of capital intensity versus R&D intensity. The more those curves get close to each other or even start to intersect, that's when there's more scrutiny on us as a community, really. So we need to show ROI on our efforts. And so we all have tools, we all have stage gates, funnels. And this isn't really to give a tutorial on that, because I know you guys all know that, you're all using it. It's really how we can modify it or tweak it to maybe squeeze some efficiency out of it. So there haven't really been much change. There hasn't been a ton of change. Luckily, we have speakers like Talia from IBM today, who's going to talk about bringing Agile to the innovation process. So it is exciting to see some of the changes. But by and large, you don't see a tremendous amount of change in some of the processes we're all using. And as I mentioned, I'm only ambitious enough to carve out the front end of this process today for my talk and really look at how we can attack that systematically with some of these tools. So this led me to start thinking about this notion of detection theory. You can look up a definition of it, and it's really the means to measure or differentiate between information-bearing patterns, or the signal, and random patterns that distract from that information or noise. So this is a fundamental concept that's used in everything from radar to IoT to wireless communications. But one very clear application, perhaps the most mission-critical application of detection theory, is in the military. So yes, I'm going to draw an analogy to business. I'm not saying they're equal in importance by any means, but just to learn some lessons from how to think about detection and how that can apply in different realms of life. So if you're in the military, you want to be able to detect the enemy and act accordingly. That's why signal detection is of the utmost importance. There's consequences if you do it wrong. First, if there's false positives, right? This means you're distracted from real threats and you're using your resources inefficiently. Well, on the other hand, there's the chance that you miss a real signal or a false negative. So this, of course, can have catastrophic consequences in a military context. So what are the parallels, at least, that we can draw from this in a business perspective? Well, You could say enemy, but it's really about detecting the opportunity and acting accordingly. If you have false positives, I think we've all probably bet on the wrong idea at one point in our life. Poor use of resources and distraction from the real opportunities that will drive our growth. False negatives. You lose market share. You don't grow very fast, or you don't grow at all, right? So there's all these issues that all kind of wrap up into that front end of identifying the right opportunities and carrying them through to where they can actually generate products that make you money. So my premise today is really, we need better results and we need them faster. And in terms of the radar, I believe it's the people in this room and people like us who are the detection mechanism for our business. We're the radar. So how can we do better? How can we increase our chances of success? So the next stage is talking about getting systematic about discovery. We've got the 12.5% success rate, not great, right? So this will be a recurring image where we think about how we can move the needle on that meter. We've got this front end of the process with the ideation, discovery, and assessment, and we'll dive into that more. So the first place that we started when we began thinking about this problem was one, if as a group, any group, an R&D group, an innovation group, our research team, if we want to be able to say with certainty which technologies are of most interest to us, it's actually pretty challenging. There's no single repository for that. And so what we did is build a living database to which democratically, really anyone on the team can add technologies to this database. And we use data to track the trajectory or measurement, sorting and ranking those technologies. How do you sort and rank? You can do it any way you want, any metrics you want. This is just our way. We have a text signal. We talked about this at length, so I won't belabor it except to say it takes in data like patents, academic papers, funding, et cetera, really like a figure of merit for innovation. And it can generate a curve for any technology you want as long as you can define it. And this example is for machine learning and AI. So the version that you see is called the 299. So this is where we've input on the back end literally thousands of technologies, and we use data to track, sort, and rank. Okay? And that's what you get when you punch in that little website there at the bottom. And it'll move. You'll see those things move because it's constantly reassessing the data that drives that ranking. I mentioned the less sexy version behind the scenes is more like 3,000 technologies that Ari alluded to. Doesn't look as nice, but again, this is kind of that repository where we can all dump in our ideas. And again, anything can make it in as granular as you want it to be, as long as it can be defined by a search string. So this is a way to have a universal repository of technology in this case. So if you think about the power of this, this is really just about having really a kind of an equality of idea, right? You've got engineer over here, you've got researcher over here, you've got innovation person over here. How can they all track and evaluate things against the same unified list? Of course, you can do this with tools like SharePoint and other ways. We wanted to make it a little bit more data-driven in terms of how we monitor the technologies. But that's a pretty rich data set, but we need to be able to dive deeper now. So the 299 is actually pretty heavily weighted towards magnitude of activity. So lots of patents, lots of investment, lots of papers, all that drives its ranking up logically. But we wanted to look at things that were perhaps, again, this idea of weak signals, things that are below the surface, that are harder to find, not so much the obvious ones, right? And that means for something like machine learning, we wanted to catch it in the 2011 timeframe, where that curve starts to tick up. So we're looking for fast growth, we're looking for acceleration, kind of inflection point, but we don't want to wait until it hits the highest possible number, because then everybody already knows, right? So we want to filter these thousands of technologies and highlight them for rapidly growing technologies. So what we did was we filtered this for fast growth over the past 2 to 5 years. And we chose purposely technologies with lower overall volumes of patents and papers. Again, hoping to get more, at least, into the noise, as opposed to those super strong signals that everybody, again, is fairly aware of. So we did this exercise. And what fell out was kind of a fun, just examination of some of these interesting technologies that bubble up. So this is obviously very technology-centric. So we had in our thousands of technologies, one that popped up was battery recycling. So battery recycling is the idea of recovering high-value materials from batteries. Extremely relevant with the proliferation of lithium-ion batteries, both in consumer electronics, but also, of course, electric vehicles. So there's end-of-life concerns as we proliferate these batteries. There's also issues of material scarcity and cost. If we can recover these materials economically, perhaps we can drive down the overall cost of battery manufacturing. Look at the data. It's got that telltale sign where it's starting to tick up in the early stages. So that's good. That kind of confirms the analysis we did. You can look at the data inside these measurements, and you can see that there's been a pretty large, almost 60% CAGR of patents over the past 3 years. But obviously, we have this whole research team. We're not going to just blindly follow the data. We're going to actually then use the expertise from our analysts to dive in to what's interesting in battery recycling, who is interesting. So this is where there's always a handoff from the data to the person, which I think should comfort us all to some extent. So my colleague, Tim Graytak, who leads our research in this area, he actually put together this diagram that looks at the value chain for battery manufacturing, but also where different recycling technologies fit back into the value chain. On top of that, he actually could put a value to the materials that are coming back out to tell you if you can recover materials below this cost, then you might have a business case, right? So again, we want to take the fact that, oh, great, the data told us battery recycling is interesting. We want to dive in. We want to understand the nuances between mechanical versus pyrometallurgical recycling, right? Those are the things that we're trying to get the data to get started, dive in with the analysis. So you can dig in further. You can dig into who is interesting. So we've identified different types of recycling, different technologies. We can then identify a company to see who we actually like and who we might engage with. So we have Onto Technologies, which is developing a process for direct battery recycling, meaning they're actually recovering entire electrode materials rather than raw materials. And their business model is actually to recover materials from the manufacturing process in something called new scrap, so stuff that goes through the manufacturing process but gets left on the cutting room floor, essentially. So if you go deeper beyond the data, you can think about, well, what should you do in this space? If the data tells me this is something that's important, what you can do is look at these technologies, look at that diagram in the upper right, and say, I'm going to segment my strategy. Direct recycling is optimal, like what Onto develops for manufacturing. So that's a great way to insert into the manufacturing process, recover, and drive down costs. But if you got batteries in a landfill, for example, you want to go with something like hydrometallurgical recycling, which is the best bet for end-of-life technology. So again, we want to get deeper under the covers with some of these technologies. The second technology that bubbled up in this analysis was transfer learning. I think we all know about machine learning. Many of you may have heard of transfer learning. I don't know how many of you are actually using it. But the idea here is the reuse of pre-trained models for a new problem or a new model. Okay? And this is extremely powerful because it can accelerate the development of models for new applications. Everybody wants to use machine learning. When you start to try and do it, you find that you need a lot of data. I was going to use a curse word, but you need a lot of data to train those models effectively. Again, that telltale sign. We can look at machine learning. We can drill in and look at something more specific like transfer learning. It's got, again, that fingerprint, I like to call it, in terms of the acceleration of the tech signal. A huge influx of patents over the past 3 years. So again, all signs are pointing to this is something worth me understanding, worth me possibly acting on. So you saw a picture on that last slide of my colleague Cole McCollum, who has led the research in this area. And he did a whole report. If you haven't seen it, I encourage you to look at it. That really dives into how to get the best results out of some of your AI initiatives. Everybody wants to do it. It's really unclear where to start in many cases, and that's what that whole report's about. But in it, he addresses specifically transfer learning. And what it addresses is a specific challenge of small data sets. If you have small data sets, you have poorly trained algorithms. If you have poorly trained algorithms, you have bad results. Okay? Where's the stage of development? It's being used in places like computer vision, but it hasn't been broadly spread to many other applications. So it's kind of in this middle stage of development. There's a number of companies that are working on this. NanoNets, 4Paradigm in China. So they're really looking at how can I take a model that's been trained for X, use some of that to help me get faster to train a model for Y. And you ask Cole, he'll tell you this to your face. What's his recommendation? Is that you investigate transfer learning and deploy it if it makes sense for your problem. If you can find a complementary model, use transfer learning to try and port it over to your solution. And really consider how this can accelerate development of the algorithms and models in your portfolio or in your future portfolio. The last one comes from our agri-food research. Again, the data bubbled up skin microbiome. And this is really the study of microbes on the skin to help understand their role in different conditions to drive the development of new therapeutics. So why is it important? Well, skin is the largest organ in the human body, and it's the first line of defense against pathogens. And this is research led by my colleague Harini. So this is really a huge opportunity. Same trajectory you see on the tech signal, same acceleration of patenting that you see over the past few years. Let's go under the covers. Let's dig a little deeper. This is a direct quote from something that Harini wrote. As the gap between science and product development closes, we expect that the skin microbiome space will have a profound impact on future formulations in the beauty and personal care market. So the data may have said it's interesting. Harini's telling you it's definitely interesting, and this is definitely something to act on. How can you pursue this? Well, right now, this is really a science problem. So you can start to look at some of the cutting-edge startups like S-Biomedic, which is actually looking at the skin microbiome as it relates to acne treatment. So our take for the technology is absolutely engage. If the data says this is interesting, we've confirmed it's interesting, we want to act on it. Little is known about the science. You gotta put R&D into this to understand where the science is. And you have to engage with any perceived leaders in the space like S-Biomedic who can get you a jump start into the space. So I told you about two steps, the living database and then filtering and highlighting rapidly growing technologies. And then handing that off to a person to really verify that this is something of interest and figuring out what to do next. If I were to end the presentation here, I'd say, at least do that. We can move the needle. Then it's business as usual. Put it into your robust innovation process and move on. Do what you normally do. But I'm going to spoil it and tell you that there's more to come in the third act. But what is the impact of doing just those first two steps on speed and results? We go back to the funnel. My colleague gave me a hard time about calling these hidden, but I'd say they're the more unspoken dimensions, at least, of the innovation funnel. Is that this x-axis is actually time. So it matters how wide these stages are, because it takes time to get through them. And the other one is, you talk about the process, we don't always go back and say, well, what was the result? Obviously, we do in other avenues when we're measuring ROI. But if we have a 12.5% win rate, how do we move that needle? So we have time, we have success rate. If you layer on these two things, we see a possible benefit at the front end. One, on the ideation side, is that if you have this living database and you have a democracy of ideas, you start to have better quality of technologies or ideas going into the funnel. The other thing that happens is that if you can use the data to bubble up important candidates, you can possibly compress that discovery stage of the innovation funnel. So this is where we're looking to squeeze more efficiency and more results out of it. So we've compressed on the time axis. Hopefully, by putting better ideas in, we get better products out. So we can bump that success rate. So I mentioned you can stop there and just look at the step 3 as being business as usual. But what if you wanted to do more? What if you wanted to see if tools could take you farther? And this is where we're going to get into machine learning. Specifically, how you can augment the next step with machine learning. What else can you do here? What can machine learning really do for us? There's a tendency either to overhype it or underhype it. Either it can do everything or it can do nothing. Well, the answer is really somewhere in between. So what if I ID a space through my previous steps, my existing process, but it's pretty broad and it's general, and I don't exactly know where to start. And the example I'll use here is 2D materials. 2D materials have been made famous, if you will, by graphene, which everybody I think in here knows about. But we're starting to see an emergence of new materials that similarly have interesting electronic, mechanical, thermal, even antimicrobial properties. So why it's important today, if you ask my colleague Anthony, who leads our research in this area, it's that graphene has finally actually made it into real products, which is, it's been a long road, but at least it's making somebody money, right? At the same time, other candidates like MXenes, for example, are starting to emerge. There's a new class of two-dimensional materials with really unknown properties at this point. You can look at graphene versus the other 2D materials. Both are actually really rapidly rising on this tech signal. Again, 100x patent growth since 2008, so a tremendous amount of activity. And if we just did the conventional step 3, we'd put our smart people on the problem, start doing landscaping, deep dives, et cetera. And what we would recommend, and what we do recommend, is to reevaluate materials and suppliers with a focus on applications specifically for graphene, but also start research on new candidates to uncover the next generation of those materials. But like I said, what if you want to do more? Well, today, if I put someone on the team on this problem and said, go after 2D materials, what would they do? They might do a patent search. So we did that, and it returned 7,000 patents. Are you going to read all of those 7,000? That's not a pleasant job, and I don't think many of us want to do that. You can analyze trends in the patenting over time. That's useful. But really, what you're talking about is slicing and dicing this space, building a taxonomy, doing tens, 50, hundreds of searches, building a comprehensive landscape. And that works. But the problem is that you get very few shots on goal if you do it this way. It takes a long time, and you're inherently biased by humans, right? If I think to look at graphene for application X, or if I think of 2D materials for Y, I have to know that before I start if I'm going to do this effectively. And this is where we enter machine learning, which is to help us with this step and see if we can get a little bit farther into the process at least. So I'm going to do a super fast, super brief tutorial of how we're using machine learning. I highly recommend you talk to my colleague Ryan Dolan, whose picture will be up in a second so you can identify him. But the idea here is you got a collection of documents, a bunch of patents, for example. You put it through a black box, which we call a topic model. That's where the magic or the machine learning happens. The model outputs topics associated with that family of documents. Then you can take any document in that set and tag it to the different topics. So it's basically a weighted average across all the different topics. So what if you do this in practice with 2D materials? You have a subset of those patents. It returns about 7,000 patents when you do a general search. Our black box is called a latent Dirichlet allocation model. If you're interested, again, I encourage you to talk to Ryan. It identified 14 topics that fell out of that document set. And it tagged all the patents to those 14 topics. Okay? So that's in a nutshell, that's what happened. So why is this interesting? Well, there's Ryan's smiling face if you want to find him. Machine learning can segment identified trends and key players from a single model. Okay? It identifies important information generally without bias. It's hard to remove all bias, but it does remove a lot of the bias that goes on in this process. And it's really rich insight from a single model. I almost put at the push of a button, but Ryan would probably strangle me because it took a whole lot more work than pushing a button. But pretend it's pushing a button. Compare that to today's process where we have few shots on goal, we have long timelines, and we have human bias that works its way into our process. So what's the output of a model like this? This is, I don't expect you to read this, but basically this is the output of that, running that topic model. It's got every patent in the set ranked and weighted against every topic that the model identified. So I can sort, slice and dice all kinds of ways from a single output. There's other fun tools for visualizing topic space. So a topic, by the way, is just really comprised of a weighting of keywords. So if I highlight topic 13 here, you can see the keywords here, such as electrode, graphene, battery, cathode, lithium. If you know anything about batteries, you could identify that as energy storage, right? So it should be clear, what the model can't do is tell you that that's batteries by itself. It can tell you that this is a grouping that's important, but this is where you still need someone to eyeball this and say, oh, I understand what this means. So we did this and got a number of different topics emerge. Topic 7, fabrication, semiconductors, energy storage, one that was more chemistry-driven about oxides, MXenes, and chalcogenides. I'm going to dive in not to all of them, but just to 2 of them to kind of show you what the details look like. So a single model spit out this. We're going to look at semiconductors and transistors and energy storage. So an example of a patent in this set was integrating and isolating NFET and PFET nanosheet transistors on a substrate. So again, pretty representative of that topic. What were the key terms? Layer, gate, channel, dielectric, semiconductor. Again, pointing towards semiconductors and transistors. From that same single model, I can pull out who the leaders are in this topic only. So I can sort, slice and dice by this topic. And you get a not surprising list that includes electronics, heavyweights, TSMC, IBM, Foxconn, and so on, right? So it makes sense what it's outputting, but it also gives you a quick landscape. Then for that topic, I can look at the specific trend as it relates to that technology group. Energy storage. You see an example of a patent topic right there. The key terms, battery, cathode, anode, separator, electrochemical. Again, if you have eyes that know what they're looking at, you can quickly identify what this is talking about. Who are the leaders here? You see a different leaderboard, right? Again, same model. I just basically filtered on a different column. Nanotech Instruments. You get a couple universities, Fudan, Manchester University. So again, quick landscaping, quick way to slice and dice, really a fast way to get at who the key players are and ultimately what the trend is in that space. So if we build on energy storage again, at some point we have to hand off to a person to dig deeper. The same thing I said in the second part of this talk. So energy storage. Let's look at a real case study to see how real life compares to what models tell us. Well, my colleague Chloe Holzinger is leading our research in this area. And this particularly pertains to the use of graphene to enable silicon anodes. If you follow the battery space, silicon is the holy grail in many ways of anodes because it has very high energy capacity. The problem is it falls apart when you cycle it and you can't make it cheaply, right? So those are the 2 kind of non-starters for the technology. Now we can dive in and look at developers that might be doing something to solve some of these problems, right? So if the data says graphene is progressing in X, Y, Z, now we can actually look and see, are there real case studies that are reflecting this progress? So Nanograph is a developer of high-capacity, high-rate silicon graphene anodes for lithium-ion. They actually use a solution-processed approach, which strongly reduces cost and results in something that is cyclable. So a really exciting innovation. So our take here as a company is they have a superior technology. They've managed to use graphene in a way that enabled a technology that has really had a hard time getting off the ground, and a business model that has really enabled their success. The last one I want to point out is kind of the dangers of machine learning or where some of these processes can go wrong. So topic 5 is called footwear. That's the best thing I could name it by looking at the data in there. And an example of this was an article of footwear for snowboarding. This is the problem where you require, again, human insight to really interpret these things. So I, in good faith, thought, Maybe Nike is using graphene in composites for shoes or something like that. I don't know. Maybe. So I looked closer at this patent, and this exact verbatim quote fell out of it. And that's the term 2D material refers to anything flat, right? So it's an example of where you need to be able to interpret things, right? It's very easy to just caught up and say, oh, there's a footwear topic, and who are the leaders? And that's a waste of time. So you do need some insight to get to the bottom of these things. Now that I have this single model that has all the rankings across all the topics, I can cross-compare them. I can look at energy storage versus nanocomposites versus fab versus semiconductors. And you can start to pull out how are things trending against each other. So as I near the end here, I wanted to say, this is an example where you can augment the process. You can landscape faster, at least, and get yourself further into the process in a more efficient way by layering machine learning on to help you prioritize topics, key players, and trends. So if nothing else, I hope this gets you thinking about how machine learning might actually play a role for you. What's the impact on the innovation process itself? We already talked about how there was compression on the front end from the first step. If we are able to layer on machine learning in an effective way, now's when you really start to impact stage 2. So now you're landscaping much more efficiently, so you can actually shrink the time at which it takes to do that initial assessment. The other benefit is that if you don't have bias going into this process, you're less at risk of missing something important. So I'm postulating that if you're able to do that effectively, that should also increase your success rate. Right? So I know this is all qualitative, but it's just thinking about the potential benefits of using some of these processes. So ultimately, we do believe machine learning can get you to insight faster. It's an unbiased, quote, push-button model that can get you results that are meaningful and help accelerate you to the next step. You have to be thoughtful about it, and you have to use your insight to understand what's important and what's not. Ultimately, nobody cares if it can't get you better results. So what you have to do is be able to measure the outcomes of some of these things and see if you really do get better results. And the last thing I would say is this idea of topic modeling has a lot of power beyond just what I showed. Imagine if your data set is news and you want to do trend analysis, or academic papers and you want to look at trends in research. There's a number of different applications for this. You just kind of plug in whatever data set you want, and you can get out different types of insight. So I'm going to wrap up with 3 key points. One is I showed you how we're thinking about it. You don't have to use the ones we use. But I'd be fascinated to hear about what you're developing internally for your business, what you decide can help you. And of course, we'd love to work with anyone who's interested. But really challenge yourself to identify tools that create efficiencies and can improve results. Because, again, as the theme of this conference, I think we all need to show better results. Second thing is, machine learning is not magic, but it can help now. I joked about the push button aspect of this. If and when we do get to that, it is a game changer because you can get to this type of rapid landscaping or rapid trend analysis extremely quickly, and that's something we're really interested in. And the last thing is, I hope I also showed that data without humans to interpret it and act on it isn't super helpful. So that should mean job security for you and your teams, ultimately, and that's what you should tell your management, because data can get you pretty far, but it can't get you all the way. And so we need to think about how we monetize and how we make use of this data. And with that, I'll wrap up, and thank you guys for listening.